All right. Well, I just recorded a bunch of stuff um, and realized actually that my microphone wasn't working. So that is great. Um, Luckily, I discovered this not too long after I'd finished working on a sort of dead end. So unfortunately, you cannot see me working on this dead end, which in one sense was sort of nice, um, as an example of plenty of things that don't work. Um, but yes, that is sort of lost without the audio. One thing I do want to repeat, and one of the things that I mentioned in that recording is the following, namely the motivation for doing this. And I mentioned some of the motivations in the first video. Another motivation that I didn't mention, which I actually think is one of the important ones, or maybe the most important one, is that I'm looking for an actual interesting problem to think about. So, now I might be coming up with small problems that I can sort of solve on the spot, or maybe often not too long thinking, but the idea is to come up with a problem that might actually require some more thought. And I thought that maybe one thing that might be interesting to look at is a problem I've been thinking about, or at least that I thought about some time ago, or maybe like 5-6 years ago, that I came up with this problem. And I've never really solved it. And it might be interesting to revisit again, because I made some progress on the problem, but it's been a while, and I actually don't remember how I proved the statement. I'm actually not 100% sure what the statement was anymore. So that might be useful to revisit that, because I don't remember the details, so that might also be sort of instructive for the people watching. And maybe I can come up with some other ideas to prove related things. So that being said, let's explain what this problem is. And of course, this is quite a big deviation from what we were talking about before, because we're talking about these polynomials, Ford operators, cyclotomic polynomials, etc. But I am interested in finding a problem or working on a problem, and that also makes it fun to sort of jump around. And in fact, one of the things that got lost in this recording was me trying to investigate the cyclotomic polynomials. Really briefly, what I tried to do is I tried to evaluate the cyclotomic polynomials at all roots of unity. Now, we know that there should be 0 for primitive roots of unity, but what kind of values do they take on other roots of unity? And I was hoping, okay, maybe they evaluate the integers somehow, or maybe there's some nice structure. So I wrote some Mathematica code real quick to check that. And it didn't really seem to be any structure. So that was the dead end. Anyway, let's get back to this problem that I was talking about. So this problem I came up with was the following. I wanted to do something with groups because I thought groups were very cool at that time. Still think they are really cool, very interesting. And but I didn't really want to have like a group theoretic problem itself. I wanted to count something, and one way to count something is to assign some integer to group elements and then sum them over all group elements in your group. Okay, that is of course a little bit vague. Let's take a step back. The order of a group element G, where G, small g is in some large group G, is the smallest integer, k, that is greater than 0, such that G to the power k is identity. Now, I'll in fact be working with cyclic groups, so I can just have that k times G is 0 for abelian groups. So this is the order of a group element G. And then what I can do is, right, since this gives me integer, if I sum this over all group elements G, I get out some quantity, and I'm going to call it S of n. And I should be clear here, this is not some group G, this is really the cyclic group C sub n. Of course, I could play the same game for an arbitrary group, right? I sum the orders of the group elements. And in fact, this turns out to be an interesting quantity. If I remember correctly, there's certain statements known that if your sum of orders of your group elements is between this and this number, then your group needs to be a billion or needs to be commutative. Sorry, not commutative. And other similar statements. Let me quickly see what I can find actually. So I'm just going to search for sum of orders of group elements, and let's see what I can find. Um, yeah, they give there's some bounds known. So if you divide the wait, what is it? What am I looking at here? Okay. That's interesting. There seem to be some new papers on this that I hadn't found before. Um, okay, so that's also actually motivation to maybe look at this. Maybe some people are actually interested in this. Anyway, let's get back to the problem at hand. So let's just stick with calculating this for cyclic groups. Now, let's do this explicitly. So what I'm going to do is I am first going to write out the order, and I'm going to put here the group elements 0, 1, 2, 3, 4. Let's do it for 6. Why not? And okay, the order of 0. That's always a little bit annoying. We have to put here 1 because k needs to be greater than 0. So we get a 1 here. Now for 1, we need to, that's simple. We just got 6. Here we get 3. Here we get 2. 4, we get, let's see, that's 3. And this is 6. Am I doing that correctly? Am I doing that correctly? Yes. Yeah. And we don't include this guy because this is doing everything mod 6, right? So this is for C6. Okay, so let's sum these guys together. Then we get 1. I'm so bad at this. Now, one thing you might notice is that the sequence here, it's almost symmetric, meaning it's symmetric around 2, ignoring the 1 here. We'll get back to that in a bit. So using the symmetry, we can just sum these guys. So that's 9 times 2, right, for these guys here, plus 2. That gives us 21. Okay, so hopefully that makes sort of clear where the calculations come from. And maybe to emphasize, here we have that the order of 4 is 3 because 3 times 4 gives me 12, which is the smallest multiple of 6 that I can get. So one can express this in terms of least common multiples, or wait, let's see, what is it? It is the there's a way to express it in terms of least common multiples. I'll get to that in a bit. Let's first get back to the statement, though, that I mentioned here about this symmetric part. Okay, so first of all, we always know that the order of 0 is going to be 1. That is sort of given. Now, what I claimed is that, okay, modulo n, we have that the order of a is the same as the order of minus a. right? That's really what the symmetry says, and that's sort of obvious because, yeah, we want this to be equal to the identity, and the minus just takes us to the inverse. So that works out. That works out completely. All right. So from there we get the symmetry. Now, let's see. Let's see. Okay. Let's try to think of something. What I did is when I first found this, I calculated some of the initial values of S of n, the sum of order of elements, and I noticed that S of n is not divisible by n. And so here we can see that 21 is not divisible by 6. And I saw this for the first 15 values or something like that calculated by hand. And by that point, I was like, okay, well, let's write a quick computer script. And I checked it for numbers up to like 1,000 or something like that, or maybe up to 1,000,000. So then I thought, okay, let's try to prove this. And one observation that we can make is the following. If we know that order A is the order of minus A, then if we assume, let's say that n is odd. Let's assume n is odd. Then what we know is that if we look at our group elements, then we have here 0, 1, 2, 3, all the way up to n minus 1. And we'll have an even, let me see, yes, we have an even number of these. And so in particular, since we have this symmetry, right, we know that this part here, the sum of these orders will be the same as the sum of the orders here. We know that this quantity here, when we sum them together, will be even, right, if we look at the associated orders. But then finally, this term here will contribute a 1. And so that means actually the total thing will be even. Sorry, will be odd. Okay, so when n is odd, we know that the output, the S of n, will always be odd. Okay, well, we can also do this for the n is even case, but in that case, we need to be careful because then there's still this middle entry here. But this middle entry is exactly n over 2. But the order of n over 2 is 2, right? So in fact, no matter the input, this quantity will always be odd. There was one annoying example though where wait, what was it again? I think there's like one degenerate case. I think probably for the wait, let's see. That doesn't make sense. I wanted to say for the group of order 1, but that's a trivial group, and there we still get out 1. Let's see. So where does this argument break? Let me quickly check. Yeah. Okay. I remember there was some weird edge case, but maybe I'm mistaken. Okay. I will double check that later. But this already shows us one thing, right? If the output is always even, then we are in good business, because then wait, what? Let's see. Yes. Okay. Of course. Yes. If n is even, then it means it has a factor of 2. But since S of n is odd, it doesn't have a factor of 2. So that means indeed that if n is even, then then indeed we'd have that n does not divide S of n. So this allows us to say that when we look at the asymptotic density of the numbers to satisfy it, then we have at least at a half of the numbers satisfied. And I remember this was the first thing that I proved, and I was like, okay, great, but it's kind of a not a very strong result. I was hoping to prove it for all numbers, right? And here's sort of the sort of the spoiler, I guess. I'm not sure at which point when I was thinking about this that I realized, but I ran at a certain point this program that I had for up to like 6 million, and there I found a counterexample. So actually, the statement as is stated is not true. There are counterexamples. There are values of n such that S of n is divisible by n. But they're quite rare, right? There, at least the first counterexample appears at 6 million. And not too long after that, there's another example. So then, the statement that one could hope for is that, okay, well, maybe there's still the asymptotic density for the numbers that does hold is 1. And maybe one could prove there's still an infinite number of counterexamples, or maybe there's even just a finite number of counterexamples. I doubt that's true, but that would be nice. Now, at a certain point, I improved on the statement, this asymptotic density of a half, and I managed to improve it to about 0.9 or 0.85, something like that. That's something that I would like to talk about now, or at least try to see how much I can recover. It turns out S of n is multiplicative in the sense that, well, just in the standard number theoretic sense, meaning that S of n is completely defined by its prime factorization of n, meaning it's given by the product of, well, let me just write it out schematically what I mean. Let's use this notation. And the idea is, of course, is that this is the prime factorization of n. Now, I forgot, and so in particular, the nice thing is that this expression is sort of nice. If I plug in a prime to the power something, there's a nice simple expression. And honestly, I forgot what it was. One thing that we can do to double check is the following. We can check what happens if we plug in just a single prime here. Now, for primes, we get out very nice behavior, right? Of course, the cyclic group of prime order is very nice. And really, we know that if I look at the order of 0, okay, that's given by 1. But all the other ones, well, we can really interpret these as and these are all sort of primitive elements in the sense that each one, we can choose any one and they will be a generator. And this is exactly the same reason why for cyclotomic polynomials, they have very nice form when we have when n is prime, and that's the fact that every root is primitive, and so we just get a geometric series. Anyway, so what that means is that I just get a 1 for the identity element, and then I get p minus 1 times. So for all the other elements, the order is given by p. So this is, let's see, can we rewrite this? Oh, let me just really expand it real quick. Let's be plus 1. Okay. Now, if I remember correctly, there was a way to write this as a fraction. And when I see this, this is just an alternating geometric series. So I can think of this as this. Of course, it's not an infinite geometric series. So there's going to be let's see. Okay, I'm not too sure about this. Too much late night mental arithmetic. So I'm just going to quickly grab Wolfram Alpha to do this. Why be smart when you can be lazy, right? So, okay, well, I know what I want to have in the denominator, so that makes things easier, of course. Yeah, okay, that makes sense, or at least it checks out. Now, if I remember correctly, if I now put an k here, this should be given by 1 plus p to the 2 times k. It's 1 divided by 1 plus p. So that one can still interpret these as a type of alternating geometric series. Or I guess one can still interpret them as a geometric series, but just with a negative um, scaling. So let's quickly check this. Let's see. Well, the smallest one we can do it for is for 4. So this gives me 1. This gives me 2. This gives me 4. This gives me 4. Okay, this looks kind of boring, but whatever. So this is 8, this is 10, this is 11. Does it check out? Well, if I plug in s2 to the power 2, then with this logic, if it's correct, it's given by 2, 5. That's a large number already. Divided by 3. Let's see, this is 33. 3, which is 11. Okay, so that works. That checks out. Of course, I haven't proven this. I will probably do that in another video. What I do want to do is the following. I want to see if I can use this to reconstruct my argument. And again, it's been a long time, so I'm not sure how far I'll get. Now, let's see. I remember that I proved my statement for square-free numbers, and actually a subset of them, but let's stick with square-free numbers. The nice thing about square-free numbers is that now I just get expressions of the following form, where I don't have any exponents here. So I just get terms like this. Etc. So, okay, we only need to study expressions of this form. And I remember looking at factors of quantities like this. And I remember that I noticed that certain factors did not appear. Let's see. Okay, so if let's see, if we plug in 3 here, Okay, yes, let's put in different primes. Let's say I put in, okay, we know that we don't have to put in a 2 anywhere, because when we have a 2 anywhere, we have something even, and we know that the statement does not hold for even numbers. So that is already good. Or sorry, the statement does hold, meaning it is divisible by, it is not divisible by n does not divide s of n. Now, that was sort of the motivation. I was like, oh, okay, we see that um, even numbers we can sort of rule out. So maybe there's other, factors or types of primes that we can rule out. So let me see what happens when I evaluate this for different primes that are not 2. Okay, so let's put in 3. So this is 28 divided by 4 if I didn't make a mistake, which is this should be 7. Okay, let's put in another prime. So I'm going to now put in 5 divided by 6, and this is 21. And this is 3 times 7. Okay. Let's put in 7, 2, 3. Okay, this is going to be hard to calculate. So at this point, I'm going to switch to Mathematica. And let me share my screen, because why not? So here you can see some of the failed attempts with these cyclotomic polynomials. They give some interesting pictures, as you can see. Okay, anyway. So we have p to the 3 plus 1 divided by p. I'm not sure what's happening here. Let's remove this. It's 1. And I want to plot the prime. I'm going to make a table out of this where this is going to does it work like this? Let's see. I'm not actually not sure how to use the prime function here. Is there a way to just iterate over the first few primes? Aha, okay. Is this the way to do it? This shouldn't be, there should be like standard. Hmm. All right, well, let's quickly just go online, iterate primes, and God, it shouldn't be too hard. Oh, yeah, so, oh, okay, yeah, that makes sense. So we're gonna put here prime, and then we're gonna, okay, so we're gonna evaluate this at, so P we're gonna send to prime, and then we're gonna run the table here from n is 1 to 8. Why not? This should run. I'm not sure why it doesn't. Oh, silly. All right, here we go. Let's see, does this, of course, check out with our previous calculations? Yes, right, because we got 7 for 3, and we got 21 for 5. Actually, what I want to do here is I also want to show the factorization. Factor integer. Nice thing about Mathematica is you can just use the naive thing, and then you should quite often get the right answer anyway. It's not an exact number. That's okay, let's quickly check this function here, what it says. It's not an exact number. That's surprising. It probably doesn't recognize that it is an integer. So let me write this in the original form, or sort of the expanded form. That is surprising. Argument is not an, let's quickly check. Argument is not an exact number. X is exact number. Okay, I am not sure why it's doing that. Is there anything other that we can do? Factor. That 43 makes sense as prime. This, it's kind of weird. Are these all primes? No, that cannot be, right? Let's see. Yeah, this is divisible by 3 because it doesn't satisfy the test for whether something's divisible by 3. Something's divisible by 3 if and only if the sum of the entries, or the entry stuff, the how do you call that, the individual terms are divisible by 3. So 5 plus 7 is 12. So this is definitely divisible by 3. Okay, so this doesn't work. Okay, that's a little bit annoying. Factorize doesn't work. Let me try one thing more. I'm gonna put here 6. Oh, okay, I see. I know I was running into issues. It's because I ask it to factor an integer, but at this point it's not an integer. Right, because what this does is it evaluates p to the nth prime, but at this point it doesn't see that yet. It hasn't seen yet that I'm going to evaluate p to this prime number, so it just sees this random expression p and doesn't know what to do with it. So let's fix that. This is ugly code, of course, but I'm allowed to. Okay, there we go. Unfortunately, it gets a little bit messy, but whatever. Now, let's see. Let me remove this because that's not too important. Again, it's not as nice as I had hoped for, as in like the output, but still. It would be nice if I could add line breaks somehow. It should be good to check that out sometime, how to do it in Mathematica. All right. Now I remember the primes that were relevant here really split into two classes, namely the primes that were, I believe, plus or minus 1 modulo 4, which are always sort of the usual suspects in well, when you have primes that split into two different classes. So let's see. Let's take minus 1, 7, which is minus 1 modulo 4. And we get a 43. Now 43 is, of course, minus 1 again, modulo 4. And that's no surprise. Sorry, I mean, that is not obvious. So again, what the statement I want to look for is, okay, if I put in here a prime that is minus 1 modulo 4, then this, when I factor S of n associated to that, I should get out something that is a factor of primes that satisfy, that are minus 1 modulo 4. Okay, let's check that. This is modulo 4 again. Sorry, this is minus 1 modulo 4. This is also minus 1 modulo 4, and this is also minus 1 modulo 4. Okay, so that seems to work out. Let's do another example. Okay, so same thing here. 19 is minus 1 modulo 4. 7 is minus 1 modulo 4. 23, same thing. Oh, wait. Okay, here we run into issues. This is not true, right? Because we have 23, which is minus 1 modulo 4, minus 1 modulo 4, but this is plus 1 modulo 4. Okay. So then if this statement is true, which I sure hope it is true, then if we put in plus 1, then we should only get out minus factors of minus 1 modulo 4. Okay, so let's have a look here. We see that's indeed the case. 3 and 1. Let's see, 13. Let's see. I'm just going to be lazy. Okay. Wait. I am now getting very confused because the statement doesn't seem to hold up. Again, I wasn't sure anymore from the top of my head what the statement was, but it seems none of them now are true, which is slightly worrying. Okay, let's check it again. Here we have minus 1, we get a minus 1, we get out plus 1. Let me see if I'm not making any silly mistakes. Yes, that's plus 1. If I put in plus 1 here, get a plus 1. Okay. Maybe that was the statement. Was it necessary that all factors are divisible by plus or minus 1 modulo 4? But that there needs to be at least one factor, which also seems like a more reasonable thing to expect, I guess. That's definitely less strong of a statement, and it's still a statement that will be strong enough to prove something. Okay, so let's see. So at least I would like to recover the statement that I want to prove. Okay, let me quickly check if I can add line breaks somehow. That would definitely make my life a little bit simpler. add line breaks to table, or I guess list, I guess. Okay, I'm not sure if this is really what I'm looking for, but yeah, that only works for strings. Okay, that's definitely not what I want. Let's remove this. Let's add a few more entries though. And actually, okay, let's make my life simpler. So what I'm going to do is I am going to evaluate a table, and I only want to, let's see. So that's annoying. With no elements from table. Okay, so this is definitely not the right way to do it. Okay, maybe there's no way of doing this. So if it is one modulo 4, it outputs this. And one thing that I can do is I can also add, I think this should work. No, it does not. Okay, that's disappointing. Okay, I'm just going to use the what was proposed here. And that seems to work. Okay, I am indeed only getting primes that are 1 modulo 4, so that's good. Let's see. Okay, so here's -1. Okay, let's check. I want to check, is there one that is always -1 or +1? Modulo 4. So 1 plus 1, sorry, -1 plus 1 plus 1. Okay, so this tells, okay. Aha, okay. So I just checked this, and here we have an example of something that's +1. But it returns 2 -1 primes in the factorization of Sn. Which we see, okay, that, and here we get out something that is really +1 modulo 4. Okay, so that tells me that statement, these are not the primes we should look at, so we should look at primes that are -1 modulo 4. So we're going to play the same trick. And so hopefully this here, the statement or something similar should hold. Okay, so let's have a look. We plug in something that's -1 modulo 4, and we get out, here we get out something that is -1. Okay, so the statement then should be is that, okay, there exists at least one factor that is divisible by a prime modulo, is divisible by at least one prime that is -1 modulo 4. And this is -1 modulo 4, -1 modulo 4, This is +1, but that's fine because here we have -1 modulo 4. Okay, -1 modulo 4, -1 modulo 4, +1 modulo 4. Again, that's fine because this term here, -1 modulo 4, -1 modulo 4, +1. But this is -1 modulo 4. Is that true? Yes, that's definitely true. Okay, let's just check all of them. Why not? So -1. Okay, so we're already good. -1, so we're good. Okay, let's double check this. I am not going to do this from the top of my head. So it's -1 modulo 4. And let's see, -1. Okay, so the statement is wait. Oh, am I? Yes. Okay. So the statement is if more than S P is divisible by a prime that is -1 modulo 4. Okay. So this is the statement that I want to make. Now, how is this useful? Let's see. So let's say that we can prove this, and I remember that I proved something like this. How could we then use this? Well, if we have S of n, where n is square free, meaning that we have something, right? We get something like this. We have some P1 times P2 times S of P3, etc. Hmm. I'm actually not sure how this helps us because, okay, what does this tell us? Um, let's assume it is square. Okay. Let's see. I think I wanted to one other condition that I had is these primes. Okay, so it's square free, and that's the important condition, I guess. Not all of them are. Not all of the P sub I are satisfy. Let's see. This condition maybe it's a +1. Let's see. So somehow this is like an annoying statement because it seems like this makes it harder to prove. right? Because we're saying, oh, if this property, then we have this divisibility condition. And it's not like this statement excludes any possible things from being divisible. Hmm. Okay, let's do just an example. Um, so what we want to show, let's just look at a single prime. If we put in a let me double check. Maybe if we put in here 1 here. Okay, this might be doing this too late at night to properly think about this. Okay, let's change this back. Let's have a look. Let's say how can okay, let's just look at a single prime factor. If I look here, I have some prime factors and I want to show that this guy does not divide the product of these guys. Well, one way of showing that is that if I put in something that is mod 3 plus 1, then I only get out something that is minus 1. Sorry, plus 1 modulo 4. But that doesn't happen. For example, here. I'm honestly a little bit stuck. I hope I didn't make a mistake with something like this, right? With some of these terms here. Let me check. It's not. Okay, no, that's not it. It's most likely not it. Let me quickly switch to my iPad. Maybe that will help a little bit. So, okay, right. What we want to show is that this does not divide this. Now, let's make this simpler, let's put something in like this. But we know that this quantity here is just given by, let me write it like this. Now this quantity, again, I can factor with some different primes. Q1, K1, Q2, K2, Q3, K3, etc. And of course, if all of these are of a different type than the as in, let's say they're all +1 modulo +1 modulo 4, while P is -1 modulo 4, then we're all good. Then it's clear that we cannot divide one by the other. But that does not seem to be the case here. So I'm really not sure what is happening. Okay. Let's see. I might. This may have just been a complete misremembering from my part. I very confidently said that, oh, the primes naturally split into two. But that's maybe it's not clear why that would appear here. Why 4 would be an important number here. Well, on the other hand, if I look here, this 3 appears. So maybe I need to look at modulo 3. So I'm going to put here a 1. Okay, let's investigate here. So I now have 7, which is +1 modulo 3, which gives me something that is gives me +1 modulo 3. +1 modulo 3, this is, well, we can use the same trick as before. 1 + 5 + 7 is 13, so this is +1 modulo 3. +1 modulo 3, +1 modulo 3, +1 modulo 3, +1 modulo 3, +1 modulo 3. Let's quickly check. +1 modulo 3 as well. +1 modulo 3, plus 1 + 3 + 8. Yes, 1 is also +1 modulo 3. Okay. Only divisible. So that seems to be true now by primes that are +1 modulo 3. Okay. Let's remove this statement. Let's quickly check when we put in here a 2. So I think something analogous to that sort of breaks down. Let's see. Oh, okay. We of course get these 3 terms a lot. Okay, so something similar doesn't hold here because here I have something +1 modulo 3. This is 0 modulo 3 +1 modulo 3 +1 modulo 3. I hope we can find a +2 modulo 3 as well. Let's see, 2, 7. This is +1. This is it's almost 16. This is this is divisible by. Wait, that doesn't make sense. Wait. 5, 4, 7, is that prime? It shouldn't be, right? 9 plus 7, 16. Oh, okay. Sorry, yeah, that's not divisible by 3. That's good. But it is +1 modulo 3. Aha. Okay, maybe so that is maybe the statement. Let's double check this real quick. 919. At this point, I'm gonna be lazy. 919 mod 3 is 1. Okay, yes, that was the statement, I believe, and I'll clarify what I mean in a bit. And the final one, let's check this one. Okay. For any p, this is never divisible by primes that are plus 2 modulo 3. That at least seems to be the case now. So if I know that my n is a square-free integer such that all of its prime factors are do not have any, let's see, do not have, okay, as long as they're not all plus, let's see, this is definitely too late. Oh, my mistake. I've been doing, am I sharing my screen? Yes, I am sharing my screen, I believe. Actually, I'm not sure what you can see right now. I believe you can see my Mathematica. Let me switch back to, oh, I think I'm both sharing my screen and my iPad. That's very confusing. Okay, hopefully you can see everything. So we have that S of P is never divisible by any prime. Yes, okay, by any prime P. With this equals to 2 mod 3, which is nice, because this tells us that if there's any prime that is plus 2 modulo 3 in the factorization of a square-free integer, then we know that the statement holds. And let's see. So I will be very vague with the argument now. But the idea is that the square-free integers, they take up, their asymptotic density is 6 over pi squared, if I'm saying that, if I remember correctly. And so you can use that to exclude another quite big range of numbers. Okay, I see. So that was the argument. Of course, we haven't proved this statement, right? That S of P is never divisible by primes that are plus 2 modulo 3, but at least that's what we observe in numerics. So that would be a good thing to check for next time. But I think now would definitely be a good time to go to bed. All right.